Today, this is my talk. You see that cancer is a mini-evolution process. This morning, that Professor Shima said that evolution proceeds by two processes. One is, say, for example, individual will reproduce, and because the genome is so large, there's a sort of mistake in replication. That's a mutation, slightly different from the original type. And most of the mutants are bad, defective, somehow function less well. But sometimes some mutant has a higher survivorship or faster rate of reproduction than original type, and they tend to spread and replace. And this process of the mutation and replacement, substitution occur many, many times. And the property of the organism changes slowly. That's sort of how evolution works, as I understand current evolution biology. And this scenario can be applicable not only to the individuals who reproduce, but also cells who reproduce. And that is cancer. Very simplified picture. Let me explain probably the best studied cancer is colon cancer. Okay? Colon is composed of large number of compartments that are called crypts. There are 10,000 crypts, 10 million crypts. Okay, huge number. And within each crypt, the compartment, there are 1,000 to 4,000 cells. And among these 4,000 cells, there are 1 to 4 cells are called stem cells. Stem cells keep sort of dividing forever throughout our life. So in this case, colon case, probably every 7 days they divide. Okay? So then after some differentiated cells, they will divide finite number of times and come up to the top of the crypts, and then they will be discarded or aborted. Now, cell division per 7 days is very frequent. If you think about the person who had already 20 years old, probably every cell in colon experienced more than 1,000 times the cell division. So that it is not surprising these some of the stem cells important gene systems which is responsible for regulating the cell division might become dysfunctional and cells start dividing faster. So in a sense, it is a sort of cancer. But normally, stem cell just receive single mutant. It's not enough to become a malignant cancer. They must accumulate number of mutations. Normally, first step for cancer is a loss of tumor suppressor. I will explain this, what tumor suppressor is. And then oncogenes, and they must be able to induce the sort of blood vessels so that they will receive supply of more nutrients. This is called angiogenesis. And finally, cells become able to acquire metastasis. Normally, cells can't survive if they are detached from the parental tissue. But for these cancer cells, by mutation, they become able to detach and then sort of landed on different tissue and then still proliferating, that causing and killing the host. So in a sense that after number of mutations accumulating in the cell line, they will reach to the state that we can call malignant cancer. So we can say that carcinogenesis is an evolution process. But if we say that this is just an evolutionary process, is an analogy. But instead, we could say that the mathematical set of mathematical theories are developed for understanding of evolution process, named population genetics, is applicable to understand the process of cancer. So today I'm just showing 3 examples of this. The first one is role of chromosomal instability. Before saying that, I will say tumor suppressor is a key word in cancer biology. And tumor suppressor functions as checking the genome. So when cell division occurs, if they find out something wrong in the genome, they will stop cell division. Or sometimes that cause apoptosis, so programmed cell death. So therefore, as far as this the system, including tumor suppressor, is functioning, cancer will not occur. Okay? So the first step for cancer is a disruption of this system, or loss of tumor suppressor gene by mutation. These are named. APC is a name of tumor suppressor, which is first occurred for colon cancer. Now, this is the scheme of the tumor suppressor proposed by, say, Knudsen, predicting existence of tumor suppressor. This is a wild type healthy cell which carried two alleles of the tumor suppressor gene. One came from father, the other came from mother. Okay? Then, by slow mutation, one of these allele will be lost. So this function just like this. But then, if the second allele with tumor suppressor is lost, there is -7. Okay? 10 to the 12 means each time they produce one cell, there is some chance of cell division. So each cell division, there is a risk of this one. Therefore, in our body, huge number of cells with many kinds of the mutants, circulating. Okay? Therefore, risk of cancer is really the problem of this. Now, so therefore, I think this is a very good structure to reducing the risk of cancer. Because, for example, if this becomes mutated, they stay for a while, but they are washed out from this. They are supplied. And they have only a finite number of cell division. I think this is related to the previous talk, right? Okay. But if you think about this stem cell, if this becomes mutated, then all things becomes cancer. See? So that is chronic myeloid leukemia. And in this chronic myeloid leukemia, mechanism is very well studied. Okay? Number 9 and 22 chromosomes are experienced chromosomal translocations. Then the new sort of fusion gene is formed. Okay? This is called BCR-ABL. That code for tyrosine kinase. And that will stimulate cells to divide. Okay? In a sense, the oncogene is created by mutation. Okay? As far as we know, this is the only mutation occurring chromosomal myeloleukemia. And a single mutation is enough to cause this leukemia. Okay. So there is a very nice drug that is effective to suppress this leukemia. Okay. This is named imatinib. But is another name is a Gleevec. Gleevec is a name of soul. Okay. Okay. This is a fusion protein, oncogene, created by this mutant gene. And then this imatinib will bind here and then stop their function. Very simple. Okay? This is a number of leukemic cells, okay, measured in terms of the quantitative PCR. This is one patient, you see. Patient go to doctor, diagnosed, you suffer CML, so you have to take this drug. Okay? You see this number of days. So you can see that this is a logarithmic plot. Okay? It is a cell count, number of cells which carry this mutant. Okay? So you can see that the linear decline and the exponential declines. You see? So therefore, this drug is very effective. Very effective. This is the first molecularly targeted medicine. Sort of success stories initially. Okay? There's quite interesting that why there are two, initially fast and later, slow, but 170 patients we analyzed, all show this. Unfortunately, after 2 or 3 years, this drug is not effective because patient go with resistant cells. And if you see the number of cells increase, resurgence occur, okay, single patient. A different patient has got a different number here. This distinguish the locational point mutations occurring in this tyrosine kinase gene. Okay, so this is the typical scenario, evolutionary scenario of the drug resistance evolutions. Initially, drug is very effective to suppress the pathogens, and then pathogen mutates, and then the third mutant is no longer effective. Okay, very simple. We know all mechanisms, but we can't stop it. So one of the questions as a biologist is asking, say, this kind of question: what's the probability for when we discover one person's patient, and what's the probability she carries already resistant stem cells? In that case, the drug will not eventually effective. Or if she doesn't carry, then can cure. Okay, this is the way to calculate. Very simple model. Let me show you. When a particular patient is diagnosed, okay, we think she carried a number of stem cells. Leukemic stem cell reached to a certain number, like 10 to the 6th. Okay? So we don't know when it starts. Maybe some time ago, mutation created this leukemic stem cell. Then they will increase by stochastic process, cell division and cell death. Okay? And eventually reach to this M. And they're asking, what is the probability there is at least one or more resistant cells? Resistant cells will be created by mutation, rare mutations. Doing like this. Probability of resistance is calculated like this. R of X. If you classify the situation according to the number of sensitive cells, and then asking how many cells mutant will be created, while sensitive cells equal to X. Okay, that is calculated like this. And it's a button-less process, but explicitly calculated. And then probability for newly arrived resistant cells, what is the lineage that is going to survive until measurement? Many of them extinct. So therefore, we should calculate this one. It's calculated by branching process. And that results. Okay? Probability resistance is M is a sort of detection number. When the patient is identified as a CML, she carries M. U is a cell division per cell division, okay, mutations. F is this integral. R and D is a cell division rate, cell death rate. A and B are it's the same thing for resistant cells. This is a this is the last slide, I hope. Okay. So, for example, resistance probability increase with M, detection size. If the patient is identified at the time she carried, say, this number, 50,000, she already more than 50% chance she carried the resistant cells. But if we can identify her much earlier, like 3,000 cells, still 90% chance she does not evolve resistance. Okay? So it is very important to identify as early as possible. Okay? Now, how about this one? This is very interesting. Okay? If you compare the cancer for leukemia, in which the cell division rate is faster, fast growing and slow growing. Fast growing ones is safer in the sense that the drug still works. Slow growing cancer has a higher chance of developing resistance at the time of detection. The logic is like this. slow-growing ones, longer time diagnosis, they have more mutations. Okay. We also calculate, derive some formula describe the number of stem cells at the time, number of leukemic stem cells at the time of the detection, also distributions. The message is, cancer progression include some aspect of evolution. Of course, molecular biological knowledge is very important on the mechanism, but because the carcinogenesis includes aspect of evolution, we must know the fitness of all intermediate mutation steps, and also how the mutation rate changed, and also say population size, how population size changed.